So, what makes the conditions so bad? A lot of things. But the first one I want to talk about is this. Do you guys remember what the temperature on Mercury was like? Was Mercury hot or cold? Yeah, Mercury was hot, right? Mercury was give or take 660-ish degrees during the daytime. It gets very, very hot on average during the day. It does get cold there at night. We mentioned that. But if we were to make a guess, just based on distance from the sun, should Venus be hotter or colder than Mercury? Just based on distance from the sun. Well, which planet is closer to the sun? Mercury is closer to the sun. So if we were just going by distance from the sun, Mercury should be hotter, Venus should be colder. But as some of you already know, as I can see from some of your comments right now, Venus is hotter than Mercury. In fact, Venus is the hottest planet in our solar system by far. It is by far the hottest planet. On average, it is 200 degrees Fahrenheit hotter than Mercury is during Mercury's daytime. Okay? So that gives you roughly about 860 degrees Fahrenheit as the average temperature on Venus. And what would we expect to happen to the temperature at night on Venus? What do we expect to happen to the temperature at night? Yeah, we'd expect it to get colder, just like Mercury, just like Earth. We expect it to cool down at least a little bit, just like on Earth. But it doesn't. It stays 860 degrees at nighttime, even when the sun is not out, right? And what would we expect the poles to be like? We'd expect the poles to be colder also, but on average, basically the entire planet of Venus, all over it, all the time, is 860 degrees. And there's not really seasons. It's just hot, hot, hot all the time, all year long. So does anybody know why Venus stays hot all the time? Why is it the hottest planet? And why does nighttime or being at the poles not help? Yeah, so we're basically getting it. It's because of how the atmosphere of Venus works through something called the greenhouse effect. Okay, and have you guys heard of the greenhouse effect before? What's another planet that has a greenhouse effect? Let me put it that way. What's another planet that has a greenhouse effect happening right now? Yes, the Earth has a greenhouse effect. And before I get into this, is the greenhouse effect a bad thing in general? Is a greenhouse effect a bad thing in general? Right. In general, a greenhouse effect is not a bad thing. But like a lot of things, the greenhouse effect is one of those all things in moderation kind of things. It's a good thing that Earth has some greenhouse effect, but we don't want to have too much greenhouse effect, right? What's a good example of a place with too much greenhouse effect? I think you guys can guess this one pretty well. What's a planet with too much greenhouse effect? Yeah, Venus. Okay, now to understand, well, specifically, Venus has what we call a runaway greenhouse effect, okay? Which essentially, in simple terms, is a greenhouse effect that has gone completely out of control. We don't currently have a runaway greenhouse effect on Earth, but we have to be careful, right? So Venus is like an extreme case of what a greenhouse effect can do. Now, to understand what I'm talking about, I'm going to real quick explain how a greenhouse effect works, okay? And then I'll explain how it works on Earth, and then I'll explain how Venus is different, okay? So let me just flip over to a different device here. So I'm going to try this out. I'm not 100% sure that this is going to work for me. Let me flip this over. Oh, and of course it has frozen on me, so let me give me 1 second to reboot that program. The school let me borrow one of their document cams. Can everybody see my hand right now on the cam? Can everybody see this? Okay, good. Okay, so what I'm going to do here is I'm going to attempt to use this instead of the marker board they gave me, because you guys probably saw last time holding up that marker board was very awkward. So what I'm going to do is I'm going to draw a picture right here of the greenhouse effect to show you how it works. Okay, so let me get this going. Let me bring this down. Let's say that this is the ground. Okay, that's the ground right there. Okay, and just so you know it's the ground, here's let's give us a little tree right here. There's a little tree. Here's you. You're hanging out. Let's assume this is Earth and not Venus, or you'd be dead right here. So there's you. Let's make you kind of fancy. There we go. Give you a top hat and a monocle. And a cane. There we go. That's you out for a good night on the town. All right. Now, a greenhouse effect happens when you have certain kinds of gas in your atmosphere. And there's a lot of different kinds of gases that we call greenhouse gases. But what is the one that we're going to be talking about right now? What's the one that's relevant for both Earth and Venus here? Which greenhouse gas do people talk about all the time? Yeah, we're getting a couple of CO2s here. Carbon dioxide. CO2 and carbon dioxide are the same thing. It's just two different ways of saying it. So, essentially, in order for a particular gas to be called a greenhouse gas, it has to have a certain profile to it. Now, if you remember in lectures we had in class, we talked about how every element and every molecule has a certain fingerprint to it. And let me review what I mean by fingerprint there. Remember, every type of substance has certain wavelengths that it really likes, that it likes to absorb, and other wavelengths that it doesn't care about at all. So if you have a gas and you shine something that's part of its fingerprint on it, it wants to trap that particular wavelength of light. And if you shine a wavelength that particular gas doesn't care about, it will let that particular wavelength pass. Okay? So that's kind of a review of what we talked about like over a month ago now. Now, it turns out that substances like CO2 or carbon dioxide have a particular type of fingerprint. Specifically, that fingerprint doesn't contain very much visible light and UV light. So in other words, CO2 doesn't particularly care about visible light and UV light. There's a few wavelengths it likes in those ranges, but for the most part, it will let UV light and visible light pass, okay? But the fingerprint of a greenhouse gas like CO2 does like infrared light. Okay? So let me make sure there's not a question here. Okay. So essentially what's happening in a greenhouse gas is that it really likes infrared, doesn't so much care about visible and UV. Okay? Now, real quick question before we go further. Is infrared light a longer wavelength or a shorter wavelength than visible and UV? Is infrared longer wavelengths or shorter wavelengths than visible and UV? Just as a review. Longer. It's longer. And don't worry if you've forgotten that. It's been a while since we've been able to talk about that. So visible and UV are very short wavelengths. UV is even shorter than visible. And infrared is longer than what we can see. So what I'm going to do is I'm going to put some CO2 up in the air here. And in real life, the CO2 is not in a big layer like that. It's spread out throughout the atmosphere, okay? But just imagine it's just going to be easier for me to show you how this works if we sort of pretend it's just a layer like this. Okay, now, does anybody know what the main wavelength of light the sun is giving off? What are the main types of wavelength? The main, like the peak types of wavelength that the sun is giving off? Yep, so we got two of them, visible light and UV. So there's a reason I brought up those two types of light specifically. Our sun is giving off mainly UV and visible light. The peak is right around, the peak is invisible, but it gives off a lot of UV as well. Now, that doesn't mean it's not giving off other kinds of light, but that's just what the peak light is. So let's imagine that the sunlight is coming down in the form of visible and UV. So let me get some sunlight coming in from the top here. Sorry about my sloppy wavelength here. This is visible and UV light. Now notice the visible and UV light went right through the CO2. Why does the CO2 let the visible and UV light through? Why does it let it through? What did I just say about it a second ago? Yep, somebody just said it doesn't like them, and that's basically the answer. Remember, if a particular wavelength is part of its fingerprint, it likes it and it wants that light. And if it's not part of the fingerprint, it doesn't like that kind of light and doesn't care. So what's happened here is that the light has been allowed to go through because CO2 does not have a very significant visible and UV component to its fingerprint. Now, when that light gets to the ground, there's two things that could happen. What two things could happen to that light when it hits the ground? Right. It can be absorbed or it can be bounced back up into the sky. So it's either going to reflect off the ground or get absorbed. And some of the light will get absorbed and some of it will get bounced back into the sky. So some of it will come right back up. Okay. And some of it will get absorbed. I can't really draw absorption. So I'm going to just kind of do that. That's absorption right there. If you're drawing along with me, maybe you want to mark that as absorption right there. Okay. So here's my quick question. Which one of those two things is going to actually heat the ground up? Is it the absorption that's going to heat the ground up or the reflection that's going to heat the ground up? We're getting a couple of answers right now. That is correct. It's the absorption. So the ground really only gets heated when the light gets absorbed. If this light bounces off the ground, it actually takes the heat with it, okay? But this is still visible in UV light, and CO2 does not care about it. So what's going to happen when that light gets right here is it's just going to go right back through it again and go to space. And this is not 100% perfect. A little bit of it gets blocked on the way in and on the way out because they're... You get what I'm saying. But for the most part, it's going to let the UV in on the way in, and it's going to let it out on the way out. And if this were the entire story, this would mean there's no greenhouse effect. And Earth's temperature would be a lot colder than it is, okay? If this was the whole story of how light worked on our planet, the Earth's average temperature would be below freezing, and that would be a very bad thing for us. We wouldn't want our average temperature to be below freezing, okay? So now, here's what we got to do. We're almost done with this picture. If the ground heats up, does it want to hold on to this heat? No. It wants to get rid of it. But is the ground going to heat up enough to give off visible light? In other words, is the ground on the Earth going to heat up enough to be as hot as a light bulb? Yes or no? No. It doesn't get as hot as a light bulb. It doesn't get as hot as the sun, but it does get hot, right? And hot things tend to give off light. And if you remember, the hotter something is, the shorter the wavelength it wants to get off, or give back off. So since the ground doesn't get that hot, would we expect it to give off a longer wavelength than visible light, or a shorter wavelength than visible light? Okay, so like I just said, the hotter something is, the shorter its wavelength is going to be. So since the Earth doesn't get as hot as the sun, its wavelength will be longer than visible light, okay? And what type of light is just a little bit longer than visible light? It's infrared, like we were saying before. So essentially, the Earth tries to get rid of the heat it absorbed by giving off infrared light. So here's infrared light coming back out. So this is IR. I'll put IR here. I'll put a V and UV here. Okay. Now, what's going to happen to this infrared when it gets to the CO2, though? When this infrared hits the CO2, what's the CO2 going to say? What's it going to do? That's correct. The CO2 essentially blocks the infrared by absorbing it. So because the CO2 does have infrared in its fingerprint, a lot of infrared wavelengths in its fingerprint, it's going to take that CO2, absorb it, and essentially trap it here on the Earth for us. And it does re-emit it, so some of it goes off into space, but a lot of it is going to end up coming back down, where it will just get reabsorbed or reflect, but it's still infrared at that point, so it just keeps getting blocked when it tries to leave. So a lot of times people say that the greenhouse effect is trapping sunlight. It's not really the right way to think of it, because the sunlight is allowed in and out. What it does trap is the infrared light that the Earth tries to get rid of when it gets heated up by the sun. Okay? Now, here's my next question. There is CO2 in the air on Earth, but is the proportion of CO2 in our air very high? Is the amount of CO2 in the air on Earth a very large percent of our atmosphere? Just yes or no. It's a low percent. It's a low percent. So our atmosphere, if you remember, is mostly nitrogen and oxygen with a less than 1% CO2, give or take. And that amount of CO2 is able to trap enough infrared light to heat our planet about 50 to 60 degrees Fahrenheit, which is enough to keep us from freezing. But that shows you that a little bit of CO2 goes a long way in terms of being able to trap heat, okay? Now, it looks like we're getting a question here. So let me pause for just a second for that question. Or maybe not. Okay, so now, why is Venus different? Okay, what makes things different on Venus? So here we go. This is going to be a little bit of a long walk. The amount of CO2 in the air is what determines how well it traps heat. Oh, by the way, why do we call this a greenhouse effect? Why is this called the greenhouse effect? Yeah, because it works pretty much exactly like a greenhouse. Greenhouses are covered in glass. Their walls and ceilings are made out of mostly glass. And it turns out that glass works very much similarly to a greenhouse gas in this case, in that it lets visible light through, but glass tends to block infrared light. So sunlight is able to get into the greenhouse, but when the plants and ground and material inside the greenhouse tries to get rid of that heat in the form of infrared, that infrared light gets trapped by the glass. So it works just the same as this, okay? You probably have experienced that. Have you ever parked your car on a sunny day in the parking lot and then get into your car? What is it like? What's it like inside of your car if you had your windows up on a sunny day? Yeah, it's exactly. It is very, very, very hot. It is hot as death in your car. Even if it's hot that day, if you get into that car, it's going to be very hot because your car is like a miniature version of the greenhouse effect in that case. So if you park your car on a sunny day, the sunlight is able to come into your car in the form of visible light and UV light, but then the glass of your windows prevents the infrared light from escaping. And that's why also if you leave a little crack in the windows, it provides an area for the the infrared light to escape out your windows, and it doesn't get as hot. Okay?